proliferation of drone technology presents a new and unique series of security threats and public safety challenges. As the popularity of drones grow, their illicit capabilities continue to increase as well. Drones, such as these, are highly sophisticated and travel at high speeds with the potential to carry explosive payloads, conduct illicit surveillance, and smuggle contraband. These small and nimble aircraft are difficult to detect and differentiate from other airborne objects, such as birds and high-altitude aircraft.
A network of optoelectronic drone tracking systems dispersed around a controlled airspace may address limitations of existing warning systems and enable greater situational awareness of drones. Our team has been tasked with developing a low-cost drone tracking prototype for Ball Aerospace. This prototype system shall detect, identify, and track drones in real time while concurrently reporting information about the tracked drone to a computer interface.
The three requirement sections for a project are performance, environment, design features, and specifications. Under performance, we have the requirements elevation, drone specification, range, detection window, automatic, tracking, recognition, an optional requirement threat level, and scan rate. For environment, we have temperature and stationary requirements, and for design features and specifications, we have power, cost, display measurements, and reporting time.
Our low-cost drone tracker is split up into 4 subsystems: optical, mechanical, software, and electrical. The optical subsystem encompasses the cameras and their lenses. The mechanical subsystem includes the servo tilt mounts, the rotary stage powered by a stepper motor, and the mounting platform. The software subsystem refers to the programs our drone tracker runs autonomously. And finally, the electrical subsystem includes the laptop and all motor controllers. Here is a look at the SOLIDWORKS model of our entire assembly. As you can see, each major piece of hardware is represented with a different color on the model. One thing to note is that wiring, fasteners, and other decorative components are not displayed here.
To adequately detect and track a drone, we must first be able to image it well enough. There are 2 imaging systems in our design. The first maintains a 70-degree field of view to initially detect objects in the airspace. Once an object is found, the second imager takes a closer look at the object to determine if it's a drone or not.
The Johnson criteria was used as a guideline for how many pixels on target are needed at minimum to perform detection, recognition, and identification for a target drone. The 70-degree field of view imager is designed for the initial detection of objects as far as 220 meters away. The second imager produces a more magnified image of the objects in order to perform recognition and identification with adequate pixels on target. Finding the right camera and lens pairings to meet these pixels on target thresholds required the consideration of sensor and lens formats, size, weight, cable interface type, mount types, performance specs, and programming capabilities. The selection process simultaneously had a very heavy emphasis on budget, availability, and lead times due to industry-wide shortages of electronic components.
The mechanical subsystem must enable quick, responsive movements, while also being stable enough to not degrade the performance of our cameras imaging faraway drones. Our optical components are fastened to a rotation platform, capable of meeting our minimum scanning speed and quickly change direction with minimal jitter. We repurposed a bar stool to raise our camera plane and elegantly house and protect all electronic components.
The software is an integral part of our project, allowing us to control our cameras, motors, and ultimately to recognize and track a drone. Our software architecture is composed of 6 sections: scanning, detection, tracking, recognition, assessment, and reporting.
Upon startup, the system automatically begins scanning, with the cameras continuously rotating on the platform. When an anomalous object is detected in the sky, we move through the detection stage. In the tracking stage, the rotation and tilt motors automatically adjust to keep the object in the center of our view. Once this happens, the recognition stage then activates, and the software determines whether the object is a drone or not through our trained recognition model, which is the key component to our project. If the object is not a drone, the system will revert to the scanning stage. If the object is a drone, we will enter the evaluation stage, and the assessed drone direction, threat level, and velocity will be reported to the user in the display. For our image recognition, we needed to train our own classification model. Common models include a variety of objects, but are not often trained to recognize quadcopter drones, especially at the distance our project requires. To train our custom model, we took over 1,000 images of our drone at our maximum recognition distance and isolated the drone and the image for the software to learn from. The next step was to test our custom model on an actual video of our drone, which showed promising results. Here is an example of our preliminary recognition software recognizing a faraway drone.
Here is our graphical user interface displaying a drone detected at 220 meters away.
Our electrical assembly provides and regulates power while also sending commands from our program to our motors. For simplicity and long run times, we elected to use a standard wall outlet as our main power source. An Arduino microcontroller is used to process and execute commands from our laptop running our software.
The stepper and servo motors are controlled through serial communication using a USB cable. To safely and precisely control the stepper motor that spins our rotation platform, a DM542T stepper driver was used. This driver gave us the ability to move our platform in steps smaller than a millidegree. We utilized a signal and power node for our servo motors to remove the need of multiple power supplies.
Our analysis models were made to ensure product performance and that requirements are met. A pixels on target model was made to predict pixel counts expected for a drone of specified size and distance away, Boresight analysis to determine the field of view overlap for both imaging systems, minimum scan period and speed for our rotation platform derived from performance requirement 4.14, weight analysis to determine total load on tilt kits and rotation platform, torque analysis to calculate the needed torque from our stepper motor, and a budget analysis to maintain project expenses under $4,000. Testing for final verification is divided into 5 tests, one each for the optical, mechanical, and computer assemblies, and tests for survivability and the recognition and identification of drones.
So far, the senior design course has been a very positive learning for all of us.
Our project required a balanced blend of optical, mechanical, electrical, and computer engineering work to tackle a relevant and complex problem in today's world.
Addressing this problem with a relatively small budget pushed us to be creative, make calculated engineering and purchasing decisions, all while having fun.
We've learned how to leverage our strengths and our weaknesses to overcome the challenges we've faced and build what will be a successful project. We'll look forward to seeing you on Design Day and hope you'll enjoy our project.